We quantize the gravitational field.
All right. Well, I guess I'm going to get started here. Today's the graviton day. We get the gravitons. So where we are, we have the Einstein's equations. Which we've worked out. The first order is pi g t mu nu, and we've been doing the weak field limit. G mu nu is flat, theta mu nu plus kappa h. Okay, if we continue with this, today we're going to look a little bit at the gravity side, and we had defined T mu nu as 2 over the square root of g, variation of the action with respect to G mu nu. Did this for matter. If we took the exact same thing and did it for gravity, we would have found the other part of, so we take the variation with respect to G mu nu. We had 4 over kappa squared r mu nu minus 1/2 G mu nu r, which was Einstein's equation, plus the total derivative. And this makes a little bit of starting the argument for interpreting a T mu nu for gravity. Okay, so let's just follow that up. Let's imagine that we're writing out Einstein's equation, but now I go to the next order. So expand to order h squared. Okay. So here schematically, r mu nu minus 1/2 G mu nu r to the first power in h. So that 1 means 1 power of h. Then the next power, you take the same thing, r mu nu minus 1/2 G mu nu r, second order, and there's clearly more terms, equals 8 pi g t mu nu. Now, this guy is quadratic in h. It's a tensor. We can take this and define, I do minus 1 over 8 pi g r mu nu minus 1/2 g mu nu r2 is defined to be, so that's not squared, it's 2, second order, defined to be, let me call it little t mu nu. Okay, little t mu nu now involves h, 2 derivatives h. That's okay. The curvature involves 2 derivatives. This is a second order, so it has 2 h's, 2 derivatives. Then since we know what that first piece is, inharmonic gauge, we have box h bar mu nu equals 8 pi g t mu nu plus little t mu nu. Okay. So in this, you see that this definition of energy and momentum, gravity's energy and momentum acts as a source also. Okay. And in fact, I have it clipped onto the next page. Oh, where'd it go? Oh, it's down 2 pages. It's much too efficient. So let's just skip down to this page here. You can calculate what it is. If you're interested in looking at this in more detail, Weinberg does it a bit in his chapter that I referred to, chapter 12, if I remember. But you can look at it there. This is what it looks like. This is what I was calling T mu nu here. I have, in doing this form, done a bunch of integration by parts to put it in a nice form. You should pay attention mostly to this guy. Okay. The top line is the stuff that survives most things. You take a look at the second line. The second line involves the derivative on H, but that for plane wave graviton is going to give 0 since it's the equations of motion. So that guy vanishes, that guy vanishes. These guys here are all total derivatives. So if I take forward matrix elements, they don't contribute anything. They contribute if you're not forward. So if you come in with one momentum and go out with another, these give something. But they don't contribute anything if you go in and come out with the same momentum, okay? Because they're total derivatives. So when we're going to take matrix elements, which we'll do somewhat soon, of the energy and momentum, really you just need to do that first guy. That's the only one that plays a major role. Okay, so there it is. This also, in the end, generates the triple graviton vertex. So if you have alpha, beta, gamma, delta, mu nu there's a triple graviton vertex, which also follows from this form here, which I'll show you later today. Okay. Any questions on that part? Now, there's a bit of gravity lore here that I just want to do. You can get general relativity from an argument like this. Interactions. So this is some work that Stanley Desser did, 1970. It's published. It's reprinted, if you want to see it, as he put it in the archive, GRQC 0411-023. So you can see it there. But it's an interesting construction, and in some ways it might be an interesting particle physics-y way to start out deriving general relativity. So it starts with, you start with a massless spin 2 field. Okay, that's our H mu nu. Okay, you find the Lagrangian from that, for that. Okay, consistent Lagrangian for H mu nu. But then, and you couple it to energy and momentum. Okay, if you couple it to energy and momentum, you then say, but the Lagrangian that I have here, which is things H, 2 derivatives H, that itself can be used to get, by Noether's theorem, an energy momentum tensor. So this gives you a T mu nu for gravity. Which is of order, it's T mu nu, which is H2 derivatives H again. Then you say, well, this coupling, this changes the Lagrangian. If this couples to H also, it changes the Lagrangian. There's a new term in the Lagrangian, which is H coupled up to H2 derivatives H. Okay, then 4 is, this changes the Lagrangian. This changes T mu nu. If you derive T mu nu from this, you get a new piece, which goes like H coupled up to H D D H. Okay, so we're building up nonlinear interactions. And then you suddenly, you do a do loop, go to 4, you keep cycling around there, you keep building up more and more interactions, and Desser shows that this iteration gives you the full GR. That's sort of neat. Okay, so that you can derive the Einstein equations and Einstein action from just iterating higher and higher orders of a spin 2 field coupled up to its own energy and momentum. Okay, so it's neat. Okay. Any questions on that? No. No. Okay. Next, gravity waves. Gravitational waves. When Laura Cardinati was here, she always was insistent that we call them gravitational waves because gravity waves are things that happen in the sun. Oscillations of the sun are called gravity waves. So they have to be gravitational waves. But anyhow, for our construction here, we have, if you're in empty space, if T mu nu equals 0, our linearized Einstein equations are box H mu nu equals 0. In harmonic gauge, we've imposed harmonic gauge. D mu H mu nu equals 1/2 d mu H. H is H lambda. Lambda is the trace. Now, normally if you have symmetric H mu nu, if you have symmetric H mu nu, 4x4 symmetric gives 10 components. Okay, if you take this harmonic gauge, there's 4 separate constraints. You take, that's 4 constraints. That gets you down to 6 components. But you can, if you're in empty space, and that's sort of the normal But if you're in empty space with T mu nu equals to 0, you can actually do another gauge transformation. So there's still another in empty space. Okay, so let's just try. Let's see what the condition is. Yeah, this isn't obvious, but here's how to show that you do it. If you do a further gauge transformation, I want to stay in a harmonic gauge. So it has to satisfy the harmonic gauge condition. So if I do a gauge transformation, remember the transformed one was differed by the derivative of a vector, and it was symmetric. And on the other side, we then have 1/2 d mu h lambda lambda minus d lambda h lambda. Okay, if I look at this first term, the first term is d mu h mu nu. Then there's minus box c nu. And then the last piece is the derivative acts on c, and actually I have one notational change that I've screwed up here. This guy here, if you look up here, the mu is contracted, nu is free, so this index should be nu. And when I come down here, this should be nu copied down there. So good, that one makes sense. Now, when I'm doing this here, I get minus d nu d mu c mu. And on the other side, we have a similar term. And this guy was a factor of 2. Sorry, remember when the gauge transformation was like that, if I take the trace, I get 2c. Boy, there we go. Now it looks better. Anybody see any other mistakes? Okay. So these guys cancel. The other ones satisfy the harmonic condition to begin with. So this implies that if I do any transformation with box c nu equals to 0, I stay in harmonic gauge. Which is good. Box C equals to 0 and box H equals to 0 is compatible. So we've not done anything to damage the theory. So now we've got 4 more constraints. Okay, so to do this, let's do this. Let's choose the following. Here's a clever choice. Choose to make H nu 0 equals to 0. Okay, so we have a gauge transformation that's written up above there. We've got 4 choices. We can adjust them. So we, so H prime nu 0 is the original H nu 0 minus C nu, derivative nu C 0 minus D 0 C nu with box H equals to 0 and box C nu equals to 0. you can then adjust that. Okay. So that's going to be 4 more constraints. So we're expecting to get down to 2. Let's just see how that plays out then. So we're going down to 2 components. Okay, let's do this motion in the z direction. So we know that h mu nu then is some function h mu nu of z minus t. That's the wave equation moving in the z direction. We have the constraint d mu h mu nu, which is d0 h0 nu plus dz h nu z equals 1/2 d nu h. Okay. By doing our gauge transformation above, we've set that guy to 0. That was our extra constraint. So now we have a simpler one. But now, if nu equals 0, this one is d by dz h0z equals 1/2 d0h. But h0z has also been set equal to 0 by our gauge condition up there. d0 on a function of z minus t can't vanish because it's got a t in it. So this tells us that h vanishes. H lambda lambda equals 0. Then if we go back up here, h is 0. So in fact, that whole side for any nu is equal to 0. So then we get dz h nu z equals to 0. So that h nu z is at best a constant, which we can set equals to 0. Okay, it's not waving anyhow. All right. So where we got? We've gotten down to now what's called the transverse-traceless. TT. We have the following conditions. We've got a box, h mu nu equals to 0. We've got d mu h mu nu equals to 0 because we already have h equals to 0. And h0 nu is equal to 0 by our gauge condition. So we've got all those conditions there. Okay. So I'm going to construct these using photon polarization vectors. Okay, you'll see what that means in a minute. This is a little different than you'll see in most gravity books, but this makes the particle physics aspect look nicer. So for photons, we have a mu goes like epsilon mu e to the minus I k dot x, and there's k squared equals 0 and k dot epsilon equals 0. And I can do the same construction as I did above for the gravitons, but for photons, and also set epsilon 0 equals to 0. Okay, so for these guys, there's helicity plus and minus 1, and epsilon mu is chosen to be 1 over square root of 2, 0, 1, plus or minus I, 0 for motion in the z direction. Okay, so this satisfies the k dot epsilon equals to 0, epsilon 0 equals to 0. Okay, and it satisfies the following things. It satisfies epsilon star mu, epsilon mu equals 1. That's the normalization. Epsilon, so this might be labeled by lambda, plus or minus 1. Epsilon mu of lambda dotted into itself. No star. Okay, so here it's starred. Actually, I can even make this better. If I make that lambda lambda prime, it's delta lambda lambda prime. They're orthogonal and they're normalized. But here the thing that I want to do is if I have two lambdas with no star, okay, no complex conjugate, I get 0. Okay, let's just do it. I get 1/2, 0 for the first one, then I get minus 1 minus plus or minus I squared minus 0 equals 0. Okay, so this guy dotted into itself gives 0. Okay, those properties allow us to use it to do transverse-traceless gravitons. Here's the construction. So we take h mu nu is some amplitude epsilon mu nu e to the I k dot x. So we're looking at plane wave solutions. The equations of motion insist that k squared equals 0. That's easy to do. But the construction that's interesting here is epsilon mu nu either plus plus, well, let's do plus plus, can be taken to be epsilon mu plus epsilon nu plus, where these guys are photons, polarization. So the vectors that I wrote up above there. So you take two plus ones, that works, and likewise epsilon mu nu minus minus equals epsilon mu minus epsilon nu minus. So those are the two possible, those are the two components we were looking for. We have two solutions now. This satisfies obviously box H equals 0. It satisfies d mu h mu nu equals 0, since we have k mu epsilon mu equals 0. So if I dot into either of those indices k, I get 0. it satisfies the h lambda lambda, the traceless condition, from epsilon mu equals 0, which I pointed out up there. And it satisfies h0 nu equals 0 because the epsilons all have 0 components. Okay, so here are our two solutions. And let's just write them out. Here's epsilon mu nu plus or minus 2. This is going to be for motion in the z direction. Okay, it's 1/2. Okay, 0, 0, 0, 0, 0, 0, 0, 0. It's 1 plus or minus I plus or minus I minus 1. 0, 0, 0, 0, 0. There. Okay, if you went to a GR book, you'd see something different. GR most often has these things in terms of plus and X waves. And if you go to a gravity wave talk, you'll see these things. It's somewhat similar, but 0 around all around here. And it's a plus minus a plus a x minus ax. So on the diagonal h's and the others. These are the equivalent of linear polarizations. So those are the linear polarizations that they do. They decompose the gravity wave experiments to. The construction that I used here is like circular polarizations. For photons, these are the circular polarized. The other thing that you see on this is, I hope we get to come back to this at the end. If you look at the syllabus, you'll see that there's a bit at the end that's supposed to be on gravity is the square of a gauge theory. This construction is part of what makes it work. What you're going to see in that when we do that, if we do it, is that the gravitational amplitudes can be written as products of two gauge theory amplitudes separately written out. So let's say I'm doing scattering of a graviton off a particle. It can be written as the scattering of a photon off of a particle twice. And this construction right here is part of what allows it to work. Even the gravity polarization vector is factorized into photon polarization vector. So hopefully at the end we get to see this. Okay. So let's now use this to do gravitons. And basically what I'm going to do here is do second quantization. So again, let's do the same thing as E and M. E and M was the following. We took A mu and we decomposed it as the sum over the polarizations, integral d3p 2 pi cubed 1 over square root of 2 omega, some normalization, a of p lambda e to epsilon mu of p lambda e to the minus I p dot x. And there's the Hermitian conjugate with A daggers there. Okay, if you do that with A of P and lambda commuting with A dagger of P lambda, P prime lambda prime, giving delta lambda lambda prime 2 pi cubed delta 3 of P minus P prime. Then we calculate the energy, the Hamiltonian, 1/2 integral d3x e squared plus v squared, which you write out in terms of derivatives of A. And you grind away. This turns into sum over lambda integral d3p over 2 pi cubed. H bar, let's put it the H bar omega P, A dagger of P, A of P plus 1/2, which you throw away. We drop that guy, and we get our states. So this is how we get our states. P lambda is A dagger of P lambda on an empty state, and the Hamiltonian on P lambda is omega P lambda. Okay. Now, this gives you the eigenstates of energy. Now, it actually works out. We have all the ingredients to do the exact same thing for gravity. Let's just say it. So we would do the exact same thing. H mu nu of x would be sum over these two polarizations, plus plus and minus minus, integral d3p over 2 pi cubed, 1 over 2 omega, A of P and lambda, and we'll use these epsilon mu nu of P and lambda, minus P dot x, plus the Hermitian conjugate. We just keep using the guys from above. And then we use the T mu nu from above. It's the only piece that I need here is the minus 1/4 H alpha beta d mu d nu H alpha beta. You might think let's just write one more term. There's a 1 over 8 H d mu d nu H. You might think you want to keep that. I told you why all the others dropped out. This one also drops out because H is 0 for this guy. All the others will drop out when either when we use the equations of motion or when I integrate. Okay, so if I look at H is the integral d3x of t0, 0. I've just got that guy there. I grind away, okay? There's various steps in here. You end up using epsilon mu nu equals 0 if the polarizations are the same, and the equivalent one is it's 0 with the stars if it's not the same. Okay. No, that's a new. Thank you. Yeah, basically, what I used is there's the properties up here, this property here, and that property there. Okay. And truth in advertising, I claim I have worked out this only for the diagonal terms, to be honest. The off-diagonal ones must vanish. So there's the things I haven't done is the A dagger type pieces. There's almost always a miracle that cancels them. I haven't worked it out for this one. But I end up getting all the normalizations work out right. Integral d3p, the 2d3p is there, 2 pi cubed. I get 1 power of omega there, and then I get the A dagger p and lambda, A p and lambda, plus a half again, and I'll drop that again, where it goes through exactly like before. And in fact, if you do the whole T mu nu, if you take, so this works out fine. So you get your states just like before. Nothing really changes. You can define graviton states by second quantization. In fact, the whole T mu nu, if I do integral d3x T mu nu, you can see it's covariant there. This ends up being lambda integral d3p 2 pi cubed p mu p nu over omega A dagger A. And again, I have not worked out the off-diagonal ones. In this case, it's not as obvious. I can actually see, just having done these things explicitly for the photon, that the 0I component here is not going to have any A dagger pieces. There's a symmetry because it'll be omega over omega p vector when integrated over ends up it cancels. But I don't know the IJ piece. I can't do the IJ piece in my head. So anyway, but that's what the matrix elements look like. When you take matrix elements of this between states, we'll get that. Okay, so we've got the graviton. It's 1 over square root of. It's 1 over square root. Thank you. Yes, I catch that. That's good. It's 1 over square root of 2 omega, just like the photon. Yes. And that was required to get the right dimensions even. Okay. So now what I'd like to do next. So we've gotten gravitational waves and we turned them into gravitons. Let's go back and do weak field quantum field theory. Okay. This is setting up the Feynman rules. So what I want to get out of this is Feynman rules. And I'd like to get out the Newtonian potential by doing graviton exchange. Okay. The way I did it before, think back last class, I did it from the wave equation for a scalar particle. We took the wave equation, we did the non-relativistic reduction of the wave equation, and showed that there's a Schrodinger equation in a gravitational potential. But that's not how you do quantum field theory. You do quantum field theory, you would get, if you're doing scattering by photons, you would do photon exchange. You draw Feynman diagrams like that. So let's go back, do weak field, and turn this into a quantum field theory, where we do Feynman rules. Okay, so we're going to start with the action, which is integral d for x square root of minus g. We've got minus 2 over kappa squared r plus the Lagrangian for matter. We'll do the expansion as before. G mu nu lower is eta mu nu plus kappa h mu nu. And now we're going to keep terms, well, second, and I'm not keeping third, but I'll give you the results for doing that. If I do square root of g times 2 over kappa squared r, that's going to get an expansion of the following. It's minus 2 over kappa d mu, let's see, it's lambda sigma h lambda sigma minus box 0 h. Box 0 just means there's no h factors in that. And the next order is the following. The next order is the one that takes a little effort. It's 1/2 d lambda h mu nu d lambda h bar mu nu. I'll remind you what that is just a second. Minus 2 d lambda h bar mu lambda d sigma h bar mu sigma. Okay, h bar with the bar over it, h bar mu nu is h mu nu minus 1/2 eta mu nu h. Okay. This first piece is a total derivative. So you drop it. The second piece is not. That's this is the important piece in the action. So there's the action for H. Okay. Now, you might think we just vary that and we proceed, but we already know that if you get an equations of motion from this, varying this gives you the Einstein equation. It gives you a equation that can't be inverted unless you fix the gauge. So we're just going to go ahead and fix the gauge right now. So here's the gauge fixing piece. We're going to add to this. We're going to do this better later on. Okay. Once I have gauge fixing in Yang-Mills down, we'll do this in perfectly. But right now, what I'm adding is I'm going to add a piece with there's a coefficient there. Actually, let's make that coefficient lambda. D mu h bar mu nu d lambda h bar lambda nu. Okay, it's a scalar. Remember, the harmonic gauge condition was basically d mu h bar mu nu equals 0 with that definition of h bar. Okay. So if I take lambda equals 1 here, this is going to be harmonic gauge. And the way to verify that is just to add this in, take lambda equals to 1, do the equations of motion, you get lambda. Yes. No, I'm sorry. This is just some parameter. Okay. I started writing C, and so if you're familiar with the RC gauges in Yang-Mills, it's the same parameter as C in Yang-Mills. I switched it to lambda just because I know I have a formula coming up where I've clipped it out of a publication where they use lambda for this guy. Okay. No, actually, that's not true. So let's go back. Let's put it as C. Make it as C. That's better notation. It's not the same thing as I have in this clip coming up. Okay. So we're going to come back and do gauge fixing right with ghosts and all that stuff once we have discovered ghosts. But for now, we're just doing this simple thing. This actually simplifies the Lagrangian. The Lagrangian, so the square root of G times the Lagrangian for gravity now, it's 1/2 d mu, d lambda h mu nu, d lambda h mu nu, minus 1/4 d lambda h, and then if I add in the linearized gravity piece, I have kappa over 2 h mu nu t mu nu. This is the t mu nu of matter. Okay, and then you'd have L matter 0, no gravitons. Okay. Okay. So, and this looks sort of familiar. This looks almost the same combination of terms that you saw in that energy momentum tensor. The ones with the indices free, etc. Anyhow, what I'm going to do then is let's integrate this by parts. The first piece, so the Lagrangian starts off as 1/2 h mu nu. Then if I integrate that first one by parts, I make that box. The second one is also integrated by parts, gives box. And then there's just a bunch of tensor structure here. So let's write h alpha beta on this side here. And then there's some contractions. I'm going to write it in the following form. I mu nu alpha beta minus 1/2 eta mu nu eta alpha beta. Okay, the first one, I mu nu alpha beta, is just a notation that I like to use for it's 1/2 eta mu alpha eta nu beta plus eta mu beta eta nu alpha. It's basically the identity. It just it takes h alpha beta and turns into h mu nu. okay? Because alpha becomes mu, beta becomes nu, and then it's symmetrized, and there's a half. So this is just the identity operator in this index space. So that's the first guy, h mu nu. The second guy is the eta mu nu on h, gives me the trace, and eta alpha beta on h gives me the trace too. So those guys are just the trace terms. Okay, now, and there should be brackets around this. So it's basically box H. So if we vary this, we're going to get the usual equations of motion, box H equals something, but there's now this tensor structure around here. I want to invert that tensor. So this is basically, if I want to get a propagator, I want to invert that tensor structure also. So I want to be getting propagator. And so I want to invert this guy, I mu nu alpha beta minus 1/2 eta mu nu eta alpha beta. And so let me try to find the inverse of that, these tensor structures. I'm going to take another tensor here, I alpha beta gamma delta, and another eta alpha beta eta gamma delta. If I can find an A and a B such that this equals I mu nu gamma delta, okay, that's inverting this tensor structure here. Okay, this is the identity in operator. Here's some tensor. Here's going to be the inverse tensor. If I work out what this is A. Since I is just the identity, this becomes I mu nu gamma delta. The second piece has eta alpha beta on there. This gives me minus 1/2 A eta mu nu eta gamma delta. Again, it's the identity, so eta alpha beta dotted into it is just etas. This next piece here, B times I is plus B eta mu nu eta gamma delta. It's the identity again. And then this last term is not the identity. Eta alpha beta alpha times eta alpha beta is 4. So I have minus 2B eta mu nu eta gamma delta. So these guys cancel if A is equal to 1 and B is minus 1/2, then I get minus 1/2 here, plus 1/2 there. I get those guys canceling, and A equals 1. I get this. Okay. So this allows me to invert the wave equation. So here's going to be my propagator. Then if I define my propagator, ID alpha beta gamma delta as a function of x is the integral d4p over 2 pi to the 4th actually, let's make it d4 cubed because that's what I tend to use here. E to the minus I q dot x over q squared. And p alpha beta gamma delta is going to be this tensor. This guy, p alpha beta gamma delta, is this, what I get is, so it's 1/2 eta alpha gamma eta beta delta plus eta alpha delta eta beta gamma. That was the I piece with the half, minus a half was then the eta alpha beta eta gamma delta. Okay, have to live with it. All these tensor indices. We don't have any choice. So we have, that's how many indices we got. We're going to do it. So if I define that, then we satisfy that h alpha beta of x is integral d for x d alpha beta gamma delta of x minus d for y, x minus y, kappa over 2 t gamma delta at y. Okay. This then this satisfies this box p, sorry, times this tensor p mu nu alpha beta h alpha beta equals kappa over 2 t mu nu, which was the wave equation that follows from this Lagrangian. I should maybe have the kappa over 2 h mu nu t mu nu there. The wave equation that follows from that Lagrangian is this equation. So gives us our first Feynman rule. If I have a propagator, alpha beta gamma delta, for a graviton of momentum q, in momentum space, it's just the momentum part of this guy. It's I p alpha beta gamma delta over q squared. Okay. All right. So there's our propagator for gravitons. Let's get rid of this stuff. Then what's the coupling to graviton? Well, in fact, we have it up here. We have, equations of motion. The coupling was sitting right there. So if we want this vertex, well, this is a matter line now. This follows from the kappa over 2 h mu nu t mu nu piece. And in fact, this is just kappa over 2. So with our scalar field there, we have p mu p, t mu nu, p mu p nu. Yeah, you can, here's what it looks like. If I take this as a function of x, I was going to write out the T mu nu itself, just to remind you, but you can probably see it out of this. There's a 2 pi cubed square root of 2 omega prime. So I've now quantized these states using the second quantization for the scalars. And this matrix element is p mu p nu minus eta mu nu p dot p prime minus m squared. Actually, one of these is sorry, I've blown that. Let's be careful. I've got p and p prime still. Okay, so that's the matrix element. Perhaps I should go. I'm not going to go back and write out T mu nu itself, just because if I do, I won't get to my punchline today. But I do have to say here, the Feynman rule follows just from this piece there. We always stick these square root of 2 omegas. We move them outside. We don't count them as part of the Feynman rules. They are for the external states, and they go into the decay rates and stuff like that. The Feynman rule then for this guy follows from this matrix element it's I kappa over 2 p mu p prime nu plus p prime mu p nu. So the piece that's in the box is minus eta mu nu p dot p prime minus m squared. Okay, so you basically extract the kinematic factors there. You throw away either the p dot x and the 2 pi cubed square root of 2 omegas in getting Feynman rules. So there's the Feynman rule there. And let's see. Oh, floating here just happens to be perfectly located is the Feynman rule for the triple graviton vertex. That followed from the T mu nu way up here that I had there from that. So basically it's taking the matrix element of that guy and that's what the Feynman rule for the triple graviton vertex is. All right, good. We won't use that for a while. Let's get rid of this guy. Yeah, I'm not going to have time for that. Okay, so here's our first Feynman diagram. Let's do graviton scattering. Gravitational. We look at 2 particles interacting by gravity. There's the Feynman diagram. Okay, well, the matrix element then, matrix element for this is, now there's a I kappa over 2 at one vertex. So if this is P1, P2, P3, P4, P1, P2 plus P1, 2 mu nu nu mu. Let's forget the next piece there. Then I get I over q squared, this projection mu nu alpha beta. On the other side, I get P3, P4. Alpha beta plus dot dot dot. Okay, we can actually see that, I mean, this is the matrix element. In the forward direction, this p dot p prime minus m squared is going to vanish. So if I'm doing very non-relativistic, or if I'm doing very forward scattering, I don't have to worry about that last piece. Okay, because p, if p prime equals p, this is m squared minus m squared. Or if I do non-relativistic. Okay, if I take non-relativistic here, let's just take all of them, the p's, to be m and 0. This turns into, this matrix element is then minus kappa, oh, I needed my kappa over 2 there. Kappa squared over 4. This becomes m1 squared from these two guys. M2 squared from those guys over q squared. And I actually I'm doing my counting wrong here. There's a factor of a half from here. There's 2's from there. So it's, if you think about the 0, 0 component in P, there's a half, 1 plus 1 minus 1 in that, all those being 0, 0. These are 2's. This actually becomes kappa over 2 is really the right answer, which is, it goes like then 16 pi g m1 squared m2 squared over q squared. And then let's quickly end the, if I do the Fourier transform, 1 over q squared turns into 1 over 4 pi x minus y. If I was doing a scattering, that's that. I then also need to do, to recover my normalization, I have to put a 1 over 2e for each of the external states to get the right non-relativistic normalization. So there's actually this 1 over, it's the 1 over 2 omega for each of the 4 guys. So that turns into 1 over 4 m1, m2. And then with the 16 pi, the 4 pi from there, 4 m1, m2, we get v of r equals minus g m1, m2 over r. All right, there we go. So we recovered the old Newton's law by doing gravitational scattering, exchanging a graviton. Okay, so I have to stop there. I actually have one more thing to do in the weak field limit. I'll come back and do that. And then we'll be on to doing some advanced field theory techniques that hold outside. So I'll do background field method, heat kernel, and gauge fixing next. Okay, good. Thanks.
All right, thanks.